Yes, as Jennifer said, my name is Sam Cocking. I'm a PhD student here in the CSIC, and I'll be talking about new insights into heritage assets, specifically new sensing approaches for masonry, arch, railway, bridges. A big part of what we do in CSIC is looking at existing infrastructure. I think what's the statistic? Every year in the UK we add 0.5% to the capital value of the infrastructure we have in the UK through new construction. Had to fit that in. So it's very important that we learn to leverage existing infrastructure if we're going to meet capacity demands in the future. So on the railway network, which is what I'm looking at, masonry arch bridges make up 50% of the bridge stock. And these are all aging assets, between 100 and 150 years old, often very damaged. We don't have a very detailed understanding of how they behave under working loads, which can be challenging when it comes to repair and maintain them. But at the same time, the replacement cost is very high, both in terms of money and carbon, so we need to have a better approach, and monitoring can help us to achieve that. The typical approach Network Rail uses deflection pole monitoring for their railway bridges. They look at the vertical deflections of the arch as trains pass overhead, but that requires direct access. It often requires road closures and big diversionary routes for traffic. So they want to get away from that, and they asked us at CSIC, in collaboration with AECOM, to look at remote sensing technologies that could replace deflection pole, or at least could be used as alternatives to it. So we use this bridge, CFM5 in Yorkshire, to do that. We're also interested as researchers in the impact of geometry on behaviour of the bridges. So this is a skewed bridge. In plan it looks like this, and it's unclear intuitively whether the loads will follow the skewed span or the squared span direction. There are a number of factors that can influence this, but we can investigate this using monitoring technologies. We're also interested in other factors such as damage. At this bridge there are big cracks between the very stiff spandrel walls and the relatively less stiff brickwork arch. This leads to a phenomenon called arch pumping, where the separation between those interfaces happens and the arch deflects a lot more. This can speed up deterioration. It was the target of an intervention in 2016, but they don't know how effective that intervention was. So if we can investigate that as well, that could be useful for asset management. So together with AECOM, we looked at a number of different options, and we came up with this monitoring installation, a large number of sensors, in order to do a thorough comparison for Network Rail, look at different options. Here's a photograph showing the sensors on site, and I'm going to spend the rest of my time talking about the fibre optics. So for these, we installed fibre Bragg gratings, FBGs, which are a type of dynamic strain sensor. And normally we would look at in-plane behaviour in a little bit like this. So here we have a longitudinal crack. We're zigzagging over the crack and looking at the dynamic opening of it as a train passes overhead. Red represents strains that are principally compressive or crack closing. Blue is crack opening, or tensile strains. Oh, sorry, other way around. Red is tensile, blue is compressive. So this is a conventional approach, but we wanted to innovate on that. We came up with, first of all, FBG rosettes, which are sort of like strain gauge rosettes on the structural scale. 3 strain readings on a triangle gives you enough information to generalize the strain state as averaged over the 0.25 meter squared triangle. And if you have a number of these triangles over the bridge, you can map the principal strains, and those have magnitude and direction information, which essentially tells you the flow of force. So here, as the train moves from left to right, we expect the thrust lines in green. We're measuring on the dotted red line the intradose of the arch, and we get distributions of strain that tie up with the thrust lines. So a band of tensile strains, red strains directly under the axle load, blue strains elsewhere, and we also see the forces are following the skewed span direction. So we answered that question from earlier. Second innovation is FBG pairs. We want to measure the pumping displacement of the arch relative to the spandrel, which is this dotted line here. That's an out-of-plane movement, which we can't typically measure with FBGs, which are an in-plane technology, but instead we measure the other 2 sides of the triangle and back calculate what that short dotted line is. So if we do this at various points on the arch and convert from strain to displacement, we get this distribution of pumping displacements, largest in the middle of the bridge, dying away towards the arch haunches, which makes sense. And we can also compare this with direct measurements with conventional sensing technologies and see that we get good agreement. So that reinforces that this works. And with FPGs, you end up essentially with a quite flexible technology that you can tailor to whatever you want to measure. As I said, this was a collaboration with AECOM. We've written 3 reports so far for Network Rail, and we're working on a 4th, which will generalize these recommendations for other masonry arches on the network. We're also submitting these to Shift 2 Rail, which is a European rail research program, in order to reach a wider audience of bridge asset owners. And this is one example of a project looking at heritage masonry structures in the UK, alongside another project, the Marsh Lane Viaduct, which Harris is working on. This work is shortlisted for a number of civil engineering industry awards. We didn't win the Rail Partnership Awards. We lost to another CSIC project, so I can't be too unhappy about that. But we are shortlisted in 3 more awards, which are happening on Thursday, so wish us luck for that. And that is the end of the talk. Thank you.